donc il va vous présenter ses travaux sur tout ce qui est en lien avec le machine learning et l'optimisation des communications pour les communications. Voilà. Donc, Professeur Sobelman, the floor is yours, so you can start whenever you want.
Bonjour tout le monde. Very happy to be here today, and want to thank the University of Bordeaux and also thank the sponsor for my talk, which is the IEEE Circuits and Systems Society. So the outline of the talk is divided into three main parts. First, I'll talk about quantized neural networks, which are a way of making more efficient, computationally efficient neural networks. Then we'll talk about network architecture search, which is a way of automatically designing architectures for neural networks. And then we'll give an application of another type of machine learning, a Monte Carlo technique applied to communication system. So first of all, as we all know by now, neural networks, and in particular deep neural networks, are everywhere in our daily lives. They're used for image classification, speech recognition, self-driving cars, natural language processing, and many other applications. Just to give a brief introduction so that we're all on the same page, we'll just review the basic idea of image classifications. What happens is we have a data set of a large number of images from different classes, and these are presented to the system during the training phase. And then after the neural network is trained, we can present another image, which would be a test image, during what's called the inference phase, and then the system would determine what category or what class that test image is in. Typically, there's an output for each possible class, the output being the probability that that image is in that class. So for example, if we present this picture of a dog to the trained neural network system, it might have several outputs, maybe an output for a dog, a cat, a bicycle, and so forth. And each of these would have a probability of being in that category. And in this example, you can see that the category for the dog has the highest probability, so therefore it would determine that this was a picture of a dog. There have been some commonly used data sets for image classification. One of the earliest ones was the MNEST modified NEST, which is handwritten digits. So the digits 0 through 9 actually written out by hand. That was one of the early data sets that was used. Another early data set was the CFAR-10, Canadian Institute for Advanced Research, and these are real-world images of objects and animals. There are also 10 classes, but the classes were things like airplanes, cars, ships, trucks, and so on. And then another popular data set was the Street View house number, where this is actually photographs of the house numbers on houses and businesses. And so, again, it would be digits, the digits 0 through 9, but rather than being handwritten, these are actually pictures of the numbers that you would see on the side of houses and buildings. Now, one of the most famous image classification data sets is the ImageNet, which contains more than 14 million images that have been hand annotated and span over 20,000 categories. And the labels indicate the objects that are in the image. The annotations were done using a crowdsourcing process where a large group of people volunteered to annotate the objects in all these different images. And there was an annual contest that was run known as the ImageNet Large-Scale Visual Recognition Challenge, where researchers would submit their image classification systems and try to obtain the highest accuracy on the ImageNet. And you can actually download this data set yourself at this website, imagenet.org, that you can play around with it. Oops, sorry. Here's a typical set of images that you would find in this data set. So this is from the category called food court. And so you can see they're two completely different images, and yet they both are in the same category, namely food court. So this would be one type of thing that your image recognition system would have to identify as being a food court. So it's a very challenging kind of competition. Now, the most powerful, at least in the early days of image recognition systems, were based on these convolutional neural networks, or CNNs. So they became very dominant in the field of image recognition. And basically, they work by passing two-dimensional convolutional filter over the image and creating an output map, and then that process is repeated over subsequent layers. And the networks typically get deeper and deeper, and so there are many, many layers of these convolutional operations as the filter is scanned over the map. And in order to do this computation, it requires a large number of multiplications and additions, or we could say multiply, accumulate operations. And so it becomes very, very computationally expensive, especially when you have large images and very deep networks. One of the famous early convolutional neural networks for image recognition was AlexNet, that actually won this competition that I mentioned in the year 2012, so 10 years ago. The competition uses some metrics called the error rate, and there are two types of error rates that are commonly used. There's the top 5 error rate and the top 1 error rate. For the top 5 error rate, the classification that is predicted by the model has to be one of the top, so the actual image class has to be among one of the top 5 probabilities predicted by your model. The top 1 error rate, the prediction has to be the actual class that the image is in. So top 5 is still pretty good, but top 1 is much more difficult to achieve. But anyway, this had a top 5 error rate of 15%, which was much better than had been achieved in previous years. And at the time, it was considered a deep network, but nowadays it's considered a fairly shallow network with only 5 convolutional layers. Another network that appeared a couple of years later was the Google Net, and this had an even much better top 5 error rate of 6.67%. And this introduced the innovation of the inception module, which is shown here. So it's a combination of a parallel set of convolutions of different size, 1 by 1, 3 by 3, and 5 by 5 convolutions. And this particular Google Net had 9 of these inception modules for a total of more than 100 layers. So now one of the issues that comes up when you start getting so many layers is the computational complexity of doing the classification. And for example, AlexNet required 724 multiply accumulate operations and 3 billion memory accesses to do a classification. And furthermore, these operations are done using 32-bit floating point operands. So the energy cost for doing these classifications is very high, and if you try to apply these on battery operated or mobile applications, it becomes very problematic to be able to support this amount of computational complexity. So one of the innovations that was introduced was the idea of quantizing the data and the coefficients to smaller than 32-bit floating point numbers. Because if we can operate on smaller numbers of bits of precision, then even if we're doing a large number of multiplies and additions, the overall computational complexity will be reduced because we're operating on smaller size operands. Now, if you take this to the most extreme level, what people investigated was actually using just a one bit of information. So, in other words, instead of using 32-bit floating point numbers, we use a 1-bit quantity. It seems like an impossibly drastic simplification, and yet it actually has been shown to work pretty well. So this one bit of representation, we use a binary number, 0 and 1, but it actually is representing two arithmetic values, namely either +1 or -1. So a binary variable with a value of 1 represents the arithmetic value +1, and the binary variable 0 would represent the arithmetic value -1. So we can quantize the weights in the neural network, that is the filter weights, or we can quantize both the weights and the data values that are flowing through the network. And if we quantize both of those using this binarization method, then we end up with what's called the binary neural network, or binarized neural network. So how do we quantize this? We simply use the sign function, SIGN, not S-I-N-E, but S-I-G-N. So using the sign function, if a floating point number is positive, we quantize that to the number +1. And if the floating point number is negative, we quantize that to the number -1. Again, it seems like a drastic simplification, and yet it's been shown that it actually works out pretty well. But now the big advantage of doing this is that instead of having to do actual multiplications and additions, we can use simple logical operations such as exclusive NOR, or XNOR, and another operation called pop count, which is counts the number of ones in a multi-bit binary number. So floating point multiply and floating point add, they're drastically simpler, and so we can then contemplate mapping these deep networks onto, for example, mobile devices that have a battery power. So it's been shown that for the simple data sets that I mentioned, like MNIST, CFAR10, and Street View House Number, the binarized neural networks give performance that's almost the same as the full precision floating point, which is very surprising, but still true. On the other hand, for the more complicated data sets like the ImageNet that I showed the example of earlier, the binarized network performance is not as good as the floating point performance, but still is a fairly reasonable performance. Now, one of the issues in using the binarized networks is during the training process. If you're familiar with the training of neural networks, there's a backpropagation process which relies on calculating the gradient. But if we're using the sine function has a derivative of 0 everywhere except at the point x equals 0. So how can we use that in the backpropagation? So what people do is they use a different function during training, which is called the hard tanh function or h-tanh function, instead of the sine function to propagate the gradient backward during training. And here's a picture of what the hard tanh function is. And so you can see that has a derivative of 1 for values of the x between -1 and 1 and derivative 0 elsewhere. So it's a little more controlled than the SIGN function. And so we can use that during training. So that's one of the issues that has been resolved. Now let's take a look at how we do these logic operations on a binarized network. So remember, we're using a logic variable 1 and 0 to represent two arithmetic numbers, +1 and -1. So a bit equal to 1 represents a value +1, a bit equals 0 represents a value -1. Now, if we're multiplying values of this type, there are really only 3 possible situations. We can multiply +1 times +1, getting +1, +1 times -1, getting -1, or -1 times -1, getting +1. And so these 3 multiplications can all be represented by a simple logic function, which is the XNOR function, exclusive NOR. The exclusive NOR of the binary variable 1 and 1 is equal to 1. So that corresponds to multiplying +1 times +1. The exclusive NOR of 0 with 1 is equal to 0, and that corresponds to multiplying +1 times -1. And the exclusive NOR of 0 with 0 is 1, which again corresponds to multiplying -1 times -1. So rather than doing actual multiplications, we just use the simple XNOR logic operation. And so this is essentially replacing our floating point multiplies with a simple XNOR logic operation. So you can see the vast simplification that we're achieving. Now, suppose we want to do a matrix vector operation, which is very common in these kinds of calculations, where everything is binarized. So if we do a 3×3 times a 3×3 matrix times the 3×1 vector, everything being +1 or -1, then every element of the result vector is going to be computed as shown here. And so there are only 4 possible values that we can get. We could get +3, +1, -1, or -3. And so what we can do is we can use the following procedure then to compute every element. First, we perform bitwise XNOR operation on the 2 binary vectors, and then we simply count the number of 1s in the result binary vector. The number of possible 1s we could get would be either 3, 2, 1, or 0. And so we just make a mapping from the number of 1s to these arithmetic values. So if we get 3 1s in our result vector, that would correspond to an arithmetic value of +3. If we get 2 1s, that would correspond to the arithmetic value of 1, and so forth for 1, 1, and 0 1s. So we just have a mapping between the number of 1s in our result vector and these 4 possible arithmetic values. Counting the number of 1s in a vector is usually called the pop count operation. And we can simply use a lookup table to do this, as I mentioned. So I gave the example of 3×3 times matrix times 3×1 vector, but in general, if we have n-dimensional matrices and n-dimensional vectors, then we can just generalize the previous example as shown here. And again, we only have a certain number of possible outcomes. And these can be represented by the number of ones in the n-dimensional vector. So we can simply use the number of ones as an index into a lookup table to find the corresponding arithmetic value that it represents. And then it's even simpler than that, because after we do that, we're going to apply the sign function again, SIGN. And so we actually don't even need to know the magnitude of the number. We don't really care whether it's +3 or +1. The sign function would only care that it's a positive number. Or if it's -1 or -3, that again doesn't matter when we apply the sign function. We only care that it's a negative value. So basically, if our vectors, matrices and vectors dimension is n, if that's an odd number, like n = 3, then the first two values are going to be positive and the second two values will be negative. And if the dimension is an even number, then the first half of the values +1 are going to be positive, and the last half of the values will be negative. So it further simplifies the computation that we need to do. We just need to know, is the population count in the first half or the second half? Okay, moving on to some other deep neural networks that have been introduced. There was a famous network called ResNet that was introduced in the competition in the year 2015, and that had a top 5 error rate of 3.57%, which is actually better than the humans can do, because they actually gave the same test to humans, and of course the humans will also make some mistakes, and the error rate of the humans was actually higher than the error rate of this ResNet system. The ResNet innovation was something called the residual block, which is shown here. And so in the residual block, there was this skip connection that's shown here between the input and the output. And this actually looks fairly simple, but one of the advantages is that it allows you to make very deep networks that can still be trained. Without the skip connection, when you get to 100 or several hundred layers, the training becomes very, very difficult. But with the skip connection that was introduced by the ResNet, it was able to be trained even very, very deep networks. So the binarization method that I've been mentioning has been applied to the ResNet architecture, coming up with a binarized ResNet implementation that used a combination of 7x7, 3x3, and 1x1 convolutions. The hardware architecture diagram is shown here, and here's a summary of the performance of the binarized ResNet architecture compared to the full precision ResNet architecture on two of the simpler data sets. Now, this is not on the ImageNet, which I mentioned is more challenging, but these are two of the simpler data sets that I mentioned at the beginning, the CFAR10 and the MNIST. Now, the binarized ResNet architecture on CFAR10 had a top 1 error rate of 8.2%, whereas the full precision ResNet had a 6.87% top 1 error rate. Now, remember, we're talking about top 1 error rate, meaning that the highest probability prediction has to be correct. The previous metrics I gave were the top 5 error rate, where you had 5 chances to get the right answer. But with top 1, you have to only pick the highest probability output from your system. So, and then on the MNEST, which is an even simpler data set than CFAR10, the binarized ResNet architecture had a 2.8% top one error rate, whereas the full precision implementation with 32-bit floating point had 1.6%. So we can see that on these simpler data sets, while it's true that the full 32-bit precision implementation of ResNet has a somewhat better error rate, it's still pretty amazing that by quantizing all the way down to a single bit for the coefficients and the data can still achieve pretty amazing performance on these simpler data sets. Okay, so let's now move on to the next part of the talk, which is on network architecture search. Now, as I've given some examples of AlexNet, GoogleNet, ResNet, and so forth, these are very complicated structures that have been designed by human experts, you know, trying experiments over a long period of time to come up with powerful architectures. So the question is it possible to somehow automatically come up with these architectures rather than having to rely on humans to play around with different combinations of convolution layers and pooling layers and skip connections and so forth? Is there some kind of way that we can have a computer that will automatically search amongst a wide range of architectures and try to find very effective architectures? So this is the topic known as network architecture search, or NAS. So we use some kind of optimization procedure to have an algorithm search over a range of architectures looking for highly effective neural network architectures. So the basic idea is that you define a search space because you have to impose some kind of constraint on what are the possible range of architectures that you can have. Then you have to define some kind of search strategy that will allow you, the algorithm, to search through this space. And then you have to have a way of evaluating how effective the optimization is. And so there's a feedback loop between the search process and the performance estimation. Now, for the search space, there are two basic categories that we can consider: the macro level and the micro level. At the macro level, we can consider how layers are connected together and whether we have sequential connections between layers or skip connections and so forth. At the micro level, we can talk about the kind of cells that we could have, such as convolutional cells, pooling cells, and so forth. For the search strategy, there are various possibilities. We could try just randomly searching, which is simple, but there's really no principle working. Or we could try some well-known type of optimization strategy, such as a genetic algorithm search. In the genetic algorithm search, we map an architecture onto a population, and then the genetic algorithm will perform the typical operation of crossover and mutation, and then we select based on some kind of measure to evolve the population from one generation to the next. So the basic flowchart for a genetic algorithm in general is that we evaluate the fitness of all the individuals in the population. Then we select two parents from the population and perform crossover and mutation to create a new child. And then we repeat this process until we have enough children to create a new generation, and then we repeat the overall loop again and again. And eventually this population of individuals is creating individuals which have better and better fitness, meaning that they solve the problem more effectively. Let's see. Okay. So how do we determine the fitness for the application that we're talking about, that is a network architecture search? Well, in order to determine whether a neural network is good or not, we have to train it, and then we have to test it on the test set. So the fitness could be measured as the accuracy percentage that we obtain after training and testing. Now, this requires a huge amount of computation, because for every individual in the population, which corresponds to an architecture, we have to train that architecture, and then we have to evaluate it, the trained architecture, on the test set. So for the application of network architecture search, determining the fitness of an architecture is actually the most computationally intensive part of the process. In order to perform the crossover operation, what we do is we take some fields of an individual from one individual, and we combine that with some other fields from another individual. And the probability of selecting a parent is proportional to its relative fitness. And then for the mutation operation, we randomly change some aspect of an architecture, and we do this in order to avoid getting stuck in a local minimum as we go through our optimization process. Examples of a global mutation would be something like adding a layer or removing a layer from an architecture, or adding a skip connection or removing a skip connection. Example of a local mutation in our network architecture search would be something like changing the filter size from 3x3 to 5x5, or changing the type of pooling that's done from max pooling to some other type of pooling, for example. Okay, to give an example of how this would work, there's we considered a binarized network, so we're still using the binarization method, and we have three fully connected binarized layers together with a output layer. And the modified NIST data set was used, which again is the handwritten digits 0 through 9. In the modified NIST, the images are very simple, 28 by 28 pixels. So the input layer has 784 neurons, and then each hidden layer was given a variable set of neurons that is determined through the genetic algorithm optimization process. The output layer is fixed at 10 neurons, corresponding to the 10 possible digits 0 through 9. So the genes are encoded as the number of neurons in the hidden layer. So we allow the hidden layers to be a various number of neurons. So for example, we have the 3 hidden layers. So if the optimization is considering the first hidden layer with 200 neurons, the second hidden layer with 450 neurons, and the third hidden layer with 975 neurons, then that would be encoded in this particular way. So this would be one particular architecture that would be considered during the genetic algorithm optimization process. So here is a chart showing the evolution of the optimization process through 10 iterations. So we start out with iteration 1 at the left and going to iteration 10 at the right. And so if you look at the either the highest accuracy that's obtained, the average, or the lowest, they're all moving somewhat higher as the iterations proceed. So the genetic algorithm approach is actually finding architectures which are operating, which have higher accuracies as the optimization process proceeds, which is what we wanted to show. Okay, let's now move on to the third part of the talk, which is a different type of machine learning, and we're going to apply that to a communication application. We're going to be considering MIMO communications, MIMO being multiple antenna systems, multiple transmit antennas and multiple receive antennas. And these are being very widely used today in all sorts of applications, 4G and 5G communication systems used in Wi-Fi and some Internet of Things. These all use various forms of MIMO technology. So here's a block diagram of the overall MIMO system. So we have a transmitter with a number of antennas, number of transmit antennas, n sub t. We have a receiver with a number of receive antennas, n sub r, and then there is a possible path between every transmit antenna and every receive antenna. And those are all the lines that are shown here. And we also consider the fact that there can be additive noise introduced at every receive antenna. So you can see that there's a channel gain shown here between every possible transmit antenna and every possible receive antenna. So the transmitter is transmitting the symbols S, and the noise is a vector N, and the receiver is receiving a vector Y. So if we consider this at the baseband level, we can characterize this as a simple matrix vector model where the H is the vector of, the H is the matrix of the channel gains that I showed in the previous slide. The S, as I mentioned, is the transmitted symbol vector, N is the additive noise, and Y is the received vector. For the signal at the kth transmit antenna, a bit vector x sub k is mapped to a complex symbol using some type of modulation, for example, the QAM or quadrature amplitude modulation. If we consider an example of 16 QAM, so at each transmit antenna, then we take 4 bits, and those 4 bits are mapped to a complex constellation point as shown here. So we take 4 bits of transmit information that gets modulated to the 16 QAM constellation. So there's an I and a Q component forming these 16 points of the constellation. So if we have a spatial multiplexing system with transmit antennas and receive antennas using QAM, then we have an overall system that's shown here. We have the individual data streams. So each transmit antenna in a spatial multiplexing system is transmitting an independent stream of data. Each stream gets channel coding for protection against errors, and then it's modulated using some type of QAM system, then gets transmitted and received at the receive system, and then we have a MIMO detector, and finally a channel decoder to decode the final transmitted bits. Now, if we can use what's called the maximum likelihood estimate of the transmitted vector, we just basically try every possible transmitted symbol and try to find the one which has the minimum difference between the H matrix times a potential transmitted symbol and the received vector. So we just evaluate every possible transmitted vector and see which one matches the received symbol the best. So conceptually, this is simple and straightforward, but computationally is impractical when we have a large number of antennas and a large QAM constellation. So we typically cannot use maximum likelihood detection. As an alternative, what we're going to consider a technique called Monte Carlo tree search, which which is a well-known technique developed many, many years ago, but became very famous recently in the machine learning context when it was used by AlphaGo to defeat the world champion Go player. That system was based on a Monte Carlo tree search. So we're going to describe a Monte Carlo tree search technique to apply to the MIMO detection process. Now, in general, in Monte Carlo tree search, we construct some kind of a search tree where we're balancing two types of information. We have exploration, where we want to look at different areas of the search tree that we haven't looked at previously, and that's balanced against exploitation, where we use areas of the search that have already been shown to be good. As I'll show in the next slide, we choose a node and then we do what's called running a simulation, which means we follow a random path until we get to a terminal node, and then we need to know at the terminal node whether it's good or not. In the context of a game, that would correspond to whether we have won the game or lost the game. So here's an example of one iteration. So if we have a partial tree that we've already constructed, then we select a node, and then from that node we create a new child node. Then from that child node we run a simulation until we get to a terminal node, which would be, again, in the context of a game, whether the game is a win or a loss. Then we take that win or loss information and we propagate the information back all the way up the tree to the root of the tree, and that helps update the values that are corresponding to the different nodes of the tree. Okay, as I mentioned, we're trying to balance two factors in our search. Exploitation, which is, given our partial results that we've learned so far, we want to exploit those to explore areas of the tree that we know are already shown to be good. However, we also want to allow the possibility of exploring new areas of the tree, because that might give us an even better solution. So how do we balance the two kind of contradictory goals of exploiting what we already know to be good versus exploring new areas that might be even better? In the context of the Monte Carlo tree search, you compute a mathematical quantity called UCT, which stands for upper confidence bound for trees, which is essentially a current reward value plus a term that's inversely proportional to the number of previous visits to a node. I'm not going through all the mathematical details, but this gives you some idea of how you balance these two different contradictory aspects of exploitation and exploration. And so we compute this UCT value, and then we choose the node that has the largest UCT value as kind of a compromise between exploration and exploitation. Okay, so how do we apply this to the topic or to the application of MIMO detection? We have to define a game board somehow, and then we have to define some legal moves on that game board Then we have to define the reward function and the simulation process. So we'll consider the detection of a signal from each transmit antenna as a move of a piece on a game board. So to detect all the transmitted symbols, we have to make a number of moves equal to the number of transmit antennas. If we're using MQAM modulation, where M is 2 to the L, then that maps onto an L by L game board. And when we move a piece on that game board, it's associated with transmitting a symbol by that antenna. So during each transmit vector time, the transmitted symbols correspond to that number of pieces on the game board. And a piece moving is just moving a piece to a location on the game board. Now, one of the aspects that's different for MIMO detection is that more than one piece can occupy the same position on the game board, because it may be that more than one transmit antenna is transmitting the same symbol at the same time. Now, we, in the context of a game like an AlphaGo, they can run a simulation and determine whether the game was a win or a loss. But in the application of MIMO detection, the receiver doesn't know what the transmitted symbol was, so it can't really determine whether the game is a win or a loss. However, it can compute a score, which is the difference between the received vector and the corresponding value of the H matrix times the S matrix the S vector that's being considered. And so that can be used in place of whether it's a win or a loss. So here's an example of using this for a 16 QAM MIMO system with 4 transmit antennas. We map the problem onto a 4x4 game board. This is just a purely artificial construction to make a connection with this Monte Carlo tree search algorithm. And then we make 4 moves, which corresponds to choosing a transmitted symbol on each of the 4 transmit antennas. And this is showing the process of choosing the child node and making a simulation, calculating that quantity, and then back propagating the information back through the network. Okay, so this process was applied to the 16 QAM MIMO system with a 64x8 antenna system. And as the game proceeds through more and more evolution moves, you can see that the correct detection probability increases as the number of moves continues until we get up to almost into the 90% correct detection probability. And then there's some additional technical enhancements that were applied. And after those were applied as well, then we can compute a typical communication metric, which is the bit error rate as a function of the signal to noise ratio, which is shown here for increasing number of moves. And then this was computed for different modulations, 16 QAM, 64 QAM, and QPSK. And the result is that the bit error rate that was achieved by this Monte Carlo tree search is competitive with other well-known types of MIMO detection, but the implementation was simpler than with some of the other MIMO detection architectures. So this idea of using Monte Carlo tree search for MIMO detection, it was shown that it can perform as well as other traditional MIMO detection techniques, but with a smaller amount of hardware required in the implementation. Okay, so that brings me to the conclusion here. So I've shown that highly quantized networks, that is using binarization, just a single bit to represent the data and the coefficients can be very effective, and since it's very computationally efficient, they can be mapped onto power-limited mobile devices. I also talked about using network architecture search, such as using a genetic algorithm to automatically search for effective neural network architectures rather than having to rely on humans to design very clever types of neural network architectures. And then finally, I showed how other types of machine learning, in particular the Monte Carlo tree search, can be applied to the MIMO detection problem, and we can create VLSI architectures for MIMO detection that perform as well as other types of conventional MIMO detection, but with a smaller amount of hardware. So then, in overall summary then, I'd like to say that by applying and combining ideas from different fields, we can look at interesting applications, and we can get new and effective design approaches that hadn't been considered previously. Okay, merci beaucoup.
Thank you so much for your presentation, Professor. If the audience has some questions, we have time for us, so ask.
Thank you for this presentation. For the last slide in the second section about the accuracy. In the second section,
Network architecture search.
yes, in the last slide, you show a figure about the accuracy. Yes, here. So may I know why for the lowest accuracy you have a lot of variability?
Yeah, so the curves here are of all the different architectures that were obtained at each iteration. We plot the highest accuracy of all those architectures, the average, and the lowest accuracy. And there is a lot of noise in the lowest accuracy one, but we wouldn't be interested in that one anyway. We would be interested in either the average or the highest accuracy. So what we're doing here is we're choosing the number of neurons in each of the hidden layers. There's 3 hidden layers. And so the genetic algorithm is choosing the number of neurons in each of those 3 hidden layers. And this is from the first iteration to the 10th iteration. So it turns out to be this kind of noisy, it's not a smooth increase, it's a somewhat noisy increase, yes. Yes. Yes.
In the neural architecture search, again, you spoke about mutation. How is the mutation done? Is it purely computational, or is there someone writing parameters to check, to perceive the mutations?
Fields in so the individual describes an architecture. There are various fields in that vector, and then with some small probability, one of those fields is just going to be randomly changed to some other value. Is that your question?
Yeah, that was so.
There's a small probability that it will be mutated. Yeah, so it's just a predefined mutation probability.
Any other question?
Yes, I have one about the search strategy optimization again. What are the advantages of going for a genetic algorithm rather than a gradient-based optimization technique?
I couldn't quite hear that. Can you speak up a little bit?
Yeah. So regarding the search strategy optimization of the network. What are the advantages of going for a genetic algorithm rather than a gradient-based optimization techniques?
Genetic algorithm? Is it, what is the advantage of using the genetic algorithm?
Compared to, for example, an optimization technique that is based on reducing the gradient?
Yeah, I mean, there are many different optimization algorithms that you could consider. The genetic algorithm was just a well-known method that can be applied to almost anything. So it was easy to map that onto this system. But yeah, you could certainly consider other types of optimization algorithms, definitely.
I have a question. We saw that.
Could you speak up a little bit?
Yeah, sorry. We saw that building building the neural network and making learning, that it feels like two different fields. Do you consider that these are really separated fields, or both of them should be done by the same person or the same group? I mean, the design of the architecture and the learning process and the data.
Oh. So, yeah, so there's the design of the architecture, which is one aspect, and then there's the training and testing of that architecture. Yeah, the question is, how do people come up with these? If you look at many papers on neural network architecture, they just show these huge block diagrams, and the question is, how do you come up with this? It seems almost like a random, and people have played around with these and just see what works. So it seems like it would be reasonable to apply an optimization algorithm to search over a large set of probabilities and do the search automatically. But of course, people are clever, so you can't always discount somebody coming up with a clever architecture on their own. I'm not sure if I answered your question, but.
I think that's it for the question. So thank you again for your presentation.
Okay.
On va avoir un vrai sur une pause au café.
Merci.